a right triangle. Let's assign it to have a right angle so it's a right triangle. So that this angle is pi over 6. And I'll normalize the thing just so the hypotenuse has length 1. May as well, right? Well, I can have studied that right triangle. Let's label the other sides as being side length A and side length B. This tells me an awful lot. If I can figure out this triangle, then I can compute things about these trig functions. For example, cosine of pi over 6 will be the adjacent side length divided by the hypotenuse. There's pi over 6. The adjacent side length is A. The hypotenuse has length 1. The stuff for pi over 6 that I typed is just wrong. There's pi over 6. What's the length of the opposite side? I labeled it as B. What's the length of the hypotenuse? 1. Tangent of pi over 6 is, oh, that one's wrong too. There is no C. Is opposite over adjacent. That'll be B over A. So if I can compute A and B in this triangle, then I can figure out trig functions at pi over 6. That's the game I'm going to want to play. All right. So here's where I'll begin. Ow. Make that not happen. Do I have enough information to find the missing angle? In fact, well, I'd rather you find the missing angle, but I'll do the walk if you like. And you don't want me to get started on how to find that angle alpha? All right. So here's how to think about it. What do angles inside of a triangle have to add up to? Pi. Pi radians, all 180 degrees. Both right answers, but I think pi is the more relevant right now because everything else is in radians. So let's use that. So angles in a triangle sum to 180 degrees or pi radians. So that means we can write down an equation. Pi over 6 plus pi over 2 plus the unknown angle alpha adds up to pi. So now it's like some algebra, right? And not even like difficult algebra, I just need to subtract some things to the other side. I think the only difficult part is simplifying a fraction. So if you go and move everything to the other side and simplify that fraction, I mean, I'll see if people want me to. That look like something you can write down now? And you don't want me to do the walk? Nice. Then I will wait for you to tell me what alpha is. Give me something reasonably simplified. I hear a pi over 3. Do I hear a second for pi over 3? Wow, that was quick, so I'll wait for a few more people to do the algebra. Do I hear agreement? Do I hear any disagreement? Nice. Do I hear a call for me to do any more? Excellent. All right, so I know this angle alpha is pi over 3. And here's something that's exciting about that. That means I can also use this exact same triangle to figure out trig functions of pi over 3. Because what's the side length? What's it? Cosine first? Cosine first. Cosine is adjacent over hypotenuse. What's the hypotenuse of this triangle still? Still 1, so it's still divided by 1. What's the length of the side that's adjacent to pi over 3? B. By the exact same logic, what ratio of sides is going to give you sine of pi over 3? A over 1? I guess that's also known as A, but all the other things I see here have the 1. How about tangent? A over B. Yeah, opposite is A, adjacent is B. All right, so if I can figure out A and B, then I know all the trig functions. So there's some motivation, and here's the idea that's going to let me do that. Instead of trying to study this triangle directly, and I don't know, like, if you write this in degrees, this is what's called a 30, 60, 90 triangle. And a 30, 60, 90 triangle has, like, some side links that are links that you can just memorize. But I'm not interested in that. I want to see, like, why it's true. So, in order to see why this result that maybe some of you already know is going to happen happens, here's what I'm going to do. I'm going to take this exact triangle, and I'm going to reflect it over the line AC. So there's AC. Take this point B. I'm going to reflect it over. I'm going to call this new point D. Oh, maybe I should have used, like, P or Q, because that actually would have been, like, B upside down in the font I'm using. Missed opportunity. Anyway, let's label the things we get. This angle of pi over 6 becomes an angle down here of also pi over 6. This angle of pi over 3 also becomes an angle of pi over 3. This right angle is still a right angle, so this big triangle is still actually a triangle, like that left rightmost side is just a single side. So what do you notice about this triangle that might look useful or interesting? It's equilateral. All of the angles are the same length. All of the angles have the same size. This angle is pi over 3. This angle is pi over 3. This angle is pi over 6 plus another pi over 6. That's pi over 3. All the angles are the same. Whenever you see a triangle and all the angles are the same, the resulting triangle is called equilateral. And what's special about equilateral triangles in addition to all of the angles being the same? All the sides are the same. And I guess that's the one that, like, really is what equilateral means. Equa as in equal, lateral as in side. I guess I don't really have my Latin. All sides are the same length. So, I think we can use that to get some information. This side of the triangle has length 1. This side of the triangle has length 1. This side of the triangle, well, half of it has length B. The other half of it also has length B. Ooh, is that enough information that you can figure out B? B is a number which satisfies that B plus B is equal to 1. So 1 over 2. So the side length B is 1/2. And I'm going to go over here and now just redraw the original triangle because the diagram up there is getting a bit messy. 1/2 Gesundheit. Right angle. Hypotenuse has length 1. This side length is still A. There's a pi over 6 and a pi over 3. Cool. And maybe before we even like find A, let's just figure out what things in this thing we can now just know because we know that B is 1/2. Do we know that one? No, we can. We'd have to figure out A, and I don't want to do that yet. Do I know that one now? Yeah. Cool. So what's the sign of pi over 6? 1/2. Just 1/2. Similarly, cosine of pi over 3 is also 1/2. So that tells me some things. Pi over 6 gives you a sine, so the y value, of 1/2. Cosine of pi over 3, so the x value, is 1/2. That feel pretty good? Nice. All right. So, I guess we need to figure out A. Do we have enough information in this picture that we could figure out A? What's the relevant fact? Like, what's the fact about triangles that would let you do this? Yeah. Side length squared plus side length squared equals hypotenuse squared. This only works for right triangles, but this is our right triangle, so we can use it. So a squared plus b squared equals c squared. Oh, but 1 squared is just 1. Think you could solve that for A? Sorry, I said that wrong. Solve that for A. I'm going to sit down. Say that.
Square root 3 over 2.
Right here, square root 3, then divide by 2. Is the 2 inside the square root or outside?
It's square root 3 over outside.
Outside. Okay, cool. Anyone want me to do the walk? Cool, yeah, it's like there's a quadratic equation there to solve, and that's it. Solve that quadratic equation. I guess you get root 3 over 2. Is this enough information? So this is now enough information to do everything, right?
A square.
Oh, yeah, okay. Otherwise it wasn't a quadratic function.
Yeah.
Cool. People feeling all right? Well, we have enough information to get all the trig functions now, don't we? So what is the cosine of pi over 6? I guess it's that, right? It's the thing we just got. Oh, this one was also just A. There's another root 3 over 2. We can put those in here. All right, fair enough. We also have enough information now to compute the tangents, don't we? And maybe I'll do things this way. Like, you just need to simplify some fractions. So, I think in a perfect world, here's what I'd like. Tangent of pi over 6. Tangent of pi over 3. Compute that, simplify, tell me what you get. Or, if people want me to do like the manipulation of how to use these fractions, raise your hand and I'll do. Cool. Then I will wait. Once you have an answer for either one, I guess some of you are more isolated than others, but those of you who have people around, go ahead and make a quick comparison. Nice, let's hear it then. Tangent of pi over 6.
Root 3 over 3.
And go root 3 over 3. Do I hear a second? Nice. Tangent pi over 3. Right here, square root of 3. Nice. Cool. So here's the payoff. If you want to know why the entries that, well, how many people, when we like flashed up this units oracle a few days ago, just like immediately filled in all the blanks right then? Cool. That's fine. Well, we're going to now. This is why those entries are true. They're true because you can study a right triangle with those angles and just do some geometry and know what the answer is going to be. There are a few other examples of things where you can do such a thing. Root 3 over 3 root 3. Nice. All right. We feel pretty good about this? All right. Let's talk about what I want to start in on today. Let's talk about graphs of trig functions. Oh, and maybe I'll announce this. Extra credit available, in which you'll do the thing that I did yesterday, in which I had like this ebony level and I measured some angles and we did some computations. Do that, but at a bigger scale. Find the height of one of the buildings on campus. You get to pick which. There are a bunch of other trig functions, and they come from studying lengths in this diagram. Figure out those trig functions, and then there's like a Scientific American article that's worth reading about these other trig functions. Nice. Let's start in on graphs of the trig functions today. And instead of like graphing them from scratch, here's what I'm going to do instead. We have a bunch of values that trig functions satisfy. Let's just do a multiple choice kind of thing. One of those two is the graph of cosine, the other one is the graph of sine. I'm going to label them. This one I will label as A. This one I will label as B. One of those is sine and the other one is cosine. Given that information, which one do you think is probably the graph of cosine? Yeah. I hear B. Why?
It's because trying to remember it. I think because cosine is like starts at, I just know it starts at 1.
Oh, cool. Yeah, let's focus on that. It starts at 1. That's the same as saying cosine of 0 is 1. Right? Oh, that's information that's in the unit circle. By looking at this unit circle, cosine of 0 means rotate by 0 radians. What's the x value? 1. So that means cosine of 0 is 1. So if I plug in an input of 0, so now that I'm thinking about the graph of a function instead of the unit circle, right, the unit circle is not the graph of the trig functions. It violates the vertical line test. It's not the graph of a function. So you rotate by 0 radians, you get to an output value of 1, so cosine of 0 is 1. So the correct graph had better go through the point 0, 1. Which one of these two goes through 0, 1? That one, I guess. Nice. Let's just check some other facts. What's the cosine of pi over 2? Look at the unit circle if you got it. 0. Nice. Does this go through pi over 2, 0? Excellent. So I guess the other one better be sine. Let's check that it does the right thing. What's the sine of 0? Cool. Nice. It goes through 0, 0. What's the sine of pi over 2? Looks good. So here's the first thing I want to do with these graphs now that we have them. Anything that you can learn about a function by studying its graph, you can now learn about these functions by studying their graphs. And these are all facts that you could get by like independent means, but you could absolutely just see them by looking at the graph now. What's the maximum value that cosine takes? 1. 1. Nice. And that also agrees with the unit circle. Cosine is the x value of a point on the unit circle. What's the biggest x value you see on the unit circle? 1. So it agrees, but you can absolutely just see it visually without thinking deep about what anything means by looking at a graph. What's the max value of sine?
1.
What inputs achieve those extreme values? So, again, by looking at the graph of cosine, give me an x value that gives you that maximum output. Just one. I don't want all of them. Just give me one of them. 0 will do. Any others? Here are 2 pi. Yep, that looks good. Any others? Negative 2 pi. That one looks good. I guess that's all the ones that are depicted. Are there any others? What's another one? 4 pi, I think, seems likely. 6 pi, negative 4 pi, negative 6 pi. So it looks like so if you let k be any integer, then x equal to 2 pi k will give you the inputs that result in maximums. Does that feel pretty alright? And trig functions have the interesting property that if they do something once, they're going to do things infinitely many times. So if you ever want to, say, all of the inputs that do something with a trig function, there'll probably be some 2 pi k that shows up. Let's play the same game for sine. Give me an input that results in that maximum value for sine. Pi over 2. Do you see any others? Negative 3 pi over 2. And this is maybe a little bit harder to just read off from the graph because the rest of them don't appear on this picture, right? Do you have any intuition for where the next value where a max might occur is? I hear 3 pi over 2. Does that match up with the graph? What's the y value at positive 3 pi over 2? Negative 1. So you've accidentally given me the worst possible answer. You've minimized. There are more, right? You can see it's going to go up and it's going to turn around at some point and come back down. But maybe the best way to build that intuition is let's actually, instead of these static computer-generated graphs, I have Desmos pulled up for a different example for later on, but there's the graph of sine of x. Does this look like Desmos is right now walking in radian mode or degree mode? Radians, I think, right? Pi over 2 is 1.5-ish. When x is 1.5-ish, you get a max. Yeah, that looks good. In fact, let's see how this graph looks if we walk in. I know you can have it walk in degrees. Big button on the bottom. There's the graph of sine of x if you walk in degree mode. That looks way less interesting, doesn't it? And that's because, right, out to 10 is not very many degrees. All right. So let's just zoom a little bit to the side. So there's the first place where our max occurred. It was at pi over 2. Anyone have any intuition for where that next max might occur?
Pi over 2 plus 2 pi.
Pi over 2 plus another 2 pi? Oh, neat. I guess that'll be 5 pi over 2, but pi over 2 plus 2 pi might even be just the best answer. Oh, is that another 2 pi over from that? So it looks like another one's going to occur there. Is that another plus 2 pi?
Yeah.
Oh, nice. Okay, cool. So let's list some of these. So it looks like 5 pi over 2 was one of them, and there was a 9 pi over 2. Let's put the dot dot dots down. It looks like x equals pi over 2 plus any multiple of 2 pi. That seem pretty alright? How about minimum? What's the least value cosine cost, right? What's the least value cosine achieves by looking at the graph? -1. What about sine? Cool. Let's figure out something about the x values that results in that. All right, so cosine first, because it's the one that's listed first in this list. Give me an input that results in cosine equal to -1. Negative pi will do. Any others? Pi. And I guess like we've now used up all the information in this literal picture. So maybe if we want to build that intuition, let's use an interactive graph and just see what we see. There's the graph of cosine. Yeah, there's negative pi, -1, pi, -1. Any intuition for the next time that you'll get a cosine value of -1 is? Let's see. 3 pi, 5 pi, 3 pi, 5 pi. Based on that pattern, do you notice like a way to describe these? Like I see pi's, that's great. And what sort of number is next to pi? Odd numbers? So it's like any odd number times pi will do. So pi equals, nope, x equals odd number times pi. Or you could write this a different way. That's pi plus 2 pi k. So maybe there's like a pattern emerging. As soon as you see something happen for a trig function once, you can keep adding 2 pi's and it'll keep happening. Minimum value for sine. We got it to be -1. Let's see if a pattern holds up. Give me an x value that results in that minimum y value. I got negative pi over 2. 3 pi over 2. Pull sine back up. Let's see. There's negative pi over 2, 3 pi over 2. Any intuition for where this next one will be? Maybe the intuition is another 2 pi over from 3 pi over 2. That seems like a reasonable prediction. Add another 2 pi. So let's see, 3 pi over 2 plus another 2 pi would be like adding another 4 pi over 2. So I guess I would total to 7 pi over 2. Let's see if it works. Oh, 7 pi over 2. Ooh, so it looks like if you can list one place where the minimum occurs and add a bunch of 2 pi's, you'll get all of them. So if you start at negative pi over 2, you'll get negative pi over 2 plus 2 pi k. If you happen to start at 3 pi over 2 and added 2 pi k, you'd get 3 pi over 2 plus 2 pi k. And those really look like different answers to the question, don't they? But they're not. Whenever you're describing an infinite family of things, you might get different looking answers if you take different starting values. But those are the same family of functions. The k's are just shifted over by 1. So far, so good. Any questions right now? Nice. Next thing I want to ask is something that I think will be, well, let's see, it's either really easy if you remember how to do it, or it's impossible because you don't remember what the ones mean. Are they even or odd? Cosine first. Is cosine even, odd, or neither based on this graph? I hear even. Do I hear anyone wanting to say odd? Do I hear anyone who forgets how to test for whether a function is even or odd? Nice. It is even. Tell me why.
I just do the paper graph like this. That's not the same graph.
Ooh, so that'll tell you it's not odd. That doesn't mean it's necessarily even. But let's go through that. There are functions that are neither. So there's the graph of cosine. So in order to check if it's odd, you pin down the origin, you rotate it 180 degrees. And I did that so you don't have to. Does this now look like the graph of cosine you have in front of you? No, it's been flipped. So it's not odd. I agree, though, it is even. But how do you test if a function is even?
X equals to cosine of x.
Yeah, so you need to check if cosine x equals question mark cosine negative x. So you need to see if the original graph is the same as that graph when you make the x values negative. So that's like reflecting over the y-axis. So if I want to take the graph of cosine and just like put a mirror here, would you see the exact same thing on the left and right? Yeah, that means it's even. So let's go through the same checks for sine of x. So if you pin down the origin on the graph of sine of x and rotate by 180 degrees, do you get the same graph back? Oh, cool. So it's odd. There is one function that is both even and odd, but it's not this one, right? If you reflect sine over the y-axis, you'll get a new graph. Cool. So far, so good. All the stuff you can do with the graph, you can now do with these graphs. You can ask about where these things are increasing and decreasing. And I guess color coding is appropriate. Increasing in blue, decreasing in orange. Sine first. So if you start at the origin, does sine look like it's increasing or decreasing? If I start going to the right, do the y values go up or down? Increasing. They go up. How far to the right can I go and still have that function be increasing? When does it stop? Pi over 2. So I make it all the way to pi over 2, and then it stops increasing. How far to the left can I go and still have it be an increasing function? Negative pi over 2. I guess at pi over 2, then it starts decreasing. Oh, let's shift that over a little bit. Make that line. So I start at pi over 2, it starts decreasing. how long does it keep decreasing? 3 pi over 2, it turns around again? At 3 pi over 2, it turns around and starts increasing. How long until it stops increasing? I guess it's off the edge of the picture graph. But it'll be the same as like a place where it gets to a maximum. So where's the first maximum after 3 pi over 2? 5 pi over 2. And then now I think I'll put a dot, 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 because I think that we have enough information. Well, no, one more. Oh, cool. So remember, turning points are places where the graph changes behavior from increasing to decreasing or the opposite. So this is enough information to find a bunch of turning points. Turning points at x equals negative pi over 2, pi over 2, 3 pi over 2, 5 pi over 2, and so on. Does that feel pretty okay? Do you think you could do the same thing for cosine on your own time? So, I'm going to skip cosine as a consequence. Fill in that space on your own. It's also in the book. You can find that information by reading the relevant section in the textbook. There's one word, I've got plenty of time, that I want to introduce for these trig functions. And here's kind of what this word means, periodic. So trig functions have the property that they like do the same thing over and over again. And I guess from the unit circle that makes good sense. Cosine starts at 1. It decreases, gets to 0, decreases, cosine gets to negative 1, goes back to 0, then to 1, and then it does the same thing over again. Functions that do that are called periodic. A function is called periodic if there is a non-zero number p, so that f of x plus p is the same as f of x. So that means if you take the whole graph of the function and shift it left by some number, you get the same function back. The minimal p that does that is called the period. So let's take a look at the graph of this particular function, cosine, and let's try to figure out its period. And here's how I'll advocate doing it. There's the graph of cosine. There's the graph of the cosine of x plus p, where p is 1. Do those two graphs look like they're the exact same function? No, one of them is like shifted over. They're different. So the period is not 1. So let's just have that p grow and see how long until they start looking like they are the same. Are they the same yet? Not yet. No, yeah, no, we're fine. They're looking closer now. Looks like 6.26 is about right. It's obviously not exactly 6.26, as we could see if we zoomed in some. All right, those don't quite line up on top of each other, but what's like a number that seems promising that's about 6.26? 2 pi, right? 3.14 times 2 becomes like 6.28-ish. So let's see if 2 pi does the job. Those two look like they're dead on the nose now? Nice. And maybe we'll like zoom in some and see. Yeah, those look like they're the same graph even zoomed in this close. So by looking at this picture, the period of cosine seems to be 2 pi. Any intuition for what the period of sine should be? No wrong answers. All I want is a guess, and then we'll check it on Desmos.
pi.
I hear a pi. Let's find out. So let's pull up the Desmos again. Go back to our normal viewing window. Let's graph sine of x, a period of pi, and let's graph the sine of x plus pi. Those look like the exact same graph. So I think the period's not pi.
2 pi.
Let's try 2 pi. Look pretty good. Cool, so it looks like the period of sine is also 2 pi. And maybe that's not so surprising. The graph of sine and the graph of cosine really look like they're basically the same graph, right? One of them's shifted over by a little bit. So they should have like a lot of the same behavior, it's just shifted by a little bit. And in fact, that observation, the graph of sine and the graph of cosine, they look like they're just shifts of each other. But what does it mean? How do you doing something to a function, if I want to shift the graph horizontally by a little bit, what should I do to the function to shift it horizontally? If I want to take a graph and shift it to the right by 6, what do I do to the function? Yeah, say that or that.
You subtract 6 in the parentheses.
Subtract 6 in the parentheses. So it sure looks like, flipping to the next page now, cosine of x should be the same thing as the sine of x plus something, where that something is how far to the left should you shift sine to get cosine. And I have the graphs back. There's the graph of sine of x, there's the graph of cosine of x. By looking at the graph of sine of x, how far to the left does it look like I need to shift that to get the graph of cosine? I guess we should just try to match up some points. So let's try to how far would I need to go to get some peaks to line up? And so there's a peak, there's another peak that's pretty close. What's the address of this peak? X equals 0, y equals 1. How far to the left do I need to shift this point to get that point? Well, it's exactly the same as what the x value is. I want to get to 0. To get something that's pi over 2 to the right down to 0, I need to go to the left by pi over 2. So it sure looks like if I take this point, shift it to the left by pi over 2, I'll get to 0. If I take this point, pi comma 0, and shift it to the left by pi over 2, what x value do I land on? Yeah, right? Pi minus pi over 2 leaves you with half of a pi. Oh, neat. There's a point there. So based on just those samples, checking those points, it looks like maybe cosine of x is the same as the sine of x plus pi over 2. And that was building intuition, but a pretty small thing to check. So let's graph some things. Let's graph cosine of x and the sine of x plus pi divided by 2. Those two look like they're on top of each other? Nice. So there's another identity that you can now just know. If you have something that involves cosines and you'd like it to involve sines, one way of getting sines involved is by adding a pi over 2 in the parentheses. That's not necessarily a hugely useful thing to do algebraically, because now you've screwed up the stuff inside the parentheses, which is kind of algebraically harder to deal with. All right. So we have this periodicity, this horizontal shift between them. Another property that you can talk about periodic functions having is an amplitude. And here's the definition of the amplitude. If you have any function that does the same thing over and over again, the amplitude is given by the maximum value the function takes minus the minimum value the function takes, and then divide that by 2. And the reason for the divide by 2 is because what I really want to do is I want to say, well, how much bigger than the average value does it get? How much lower than the average value does it get? Add those two things together and divide by 2. That seem reasonable as a definition to make? All right, well, let's compute that for these things. Let's compute the amplitude of cosine x. So it'll be 1/2 times the maximum value. What's the maximum value cosine takes? 1? Minus the minimum value. What's the minimum value cosine takes? -1. Close parentheses. Oh, cool. So what's the amplitude of cosine? 1. That's another good reason to define amplitude the way I just did. Sine and cosine are like the simplest periodic functions. So they should have the simplest possible amplitude. Amplitude of sine and cosine are both 1. I guess we've just checked it for cosine, but would you write down the exact same thing for sine? Right, what's the max of sine? Min? So you do the exact same computation. Ruby. So I feel okay stopping here because in the earlier section we in fact fell way behind this point here. So stopping now is sensible from the point of view of not having the 2 sections get 2 sections. So take a look at the web walk and stuff for today. Chances are decent that I'll push the deadline back as if it were assigned on Monday because we didn't actually finish all the stuff. But you have most of the things you need to think about it. So take a look at the web walk. Yeah. You know the drill. You can shoot me any email questions. On the way out, I'm going to remind you of some things. You can have some more candy on the way out if you like. Anyone planning on coming by my office hour today? I will also have more candy probably in my office during my office hour if that impacts your decision. You don't even have to ask me questions. I'll have candy in my office if you want. Probably. I can't promise that it won't on the whole. And then there's the extra credit talk tonight. Yeah, do it. Why don't you even put waffles in the pack? Nobody likes them. Oh, okay, you can have a waffle.
Thank you.
Yeah, you're welcome. Yeah. Thank you. Enjoy. You're welcome. You too.
Thank you.
Enjoy.